Today we're going to figure out some story problems related to elastic collisions and inelastic collisions. So you'll need this paper out, and we're going to fill in all of the work onto our papers right here, the guess formula sheets. Now I know that we're not going to have enough space to write down every single given unknown, substitute and solve. So what we're going to do today is try to utilize our space as best possible, and instead of putting down the givens unknown equation, I'm going to have you instead draw some little diagrams, and we'll fill in our stuff for the givens into those diagrams. So number one, we did this in class, but I'm just going to redo it so that way we have our video. What we'll start with is the idea that says you have a 0.25 kilogram cue ball, and it's going to hit the 0.25 kilogram 8 ball. So you have the cue ball and you have the 8 ball. Now this is the before collision. All right, now they both have the exact same mass. So I'm going to put mass equals 0.25 kilograms. We're going to put 0.25 kilograms. Okay. Now the 8 ball, we have to infer this, that it's going to have a velocity of 0 before it's hit. And it says that before the collision, the cue ball has a velocity of 22 meters per second. All right, so what is our total momentum beforehand? Well, our formula, mass times velocity. You take your 0.25, and we'll have 0.25 times the 22. You've got 5.5 kilogram meter per second. We know the momentum of the 8 ball ahead of time is going to be 0 kilogram meter per second. So grand total momentum beforehand would be 5.5. Now what's going to happen is the cue ball is going to hit, bam, it's going to hit the 8 ball. Now in the question, it says that you have a perfect elastic collision. What that means is that the cue ball at first, that's the only thing that's going to be moving. The 8 ball, it's not moving. In a perfect elastic collision, what's going to happen is every last bit of momentum that the cue ball had at first is going to be given to the 8 ball. So the cue ball, upon contact, it's going to stop, and the 8 ball is going to move. So what we have to do is figure out with what velocity does that 8 ball move. So our masses for these two things, they're not going to change. So these two masses, no matter what the situation is, as long as the ball doesn't break apart, we know that it's going to still have the same mass. So our velocity for the cue ball, we said was 0 because it's a perfect elastic collision, but we don't know what this velocity right here is. Okay. So just like before, if we're trying to figure out what our momentum is, we multiply it out. We know that the cue ball afterwards, it's not going to have anything because it's resting. It's at rest. And then the 8 ball, we know the mass is 0.25 kilograms times the velocity of the cue ball after the collision. We don't know what that is. Now, law of conservation of momentum, whatever momentum that we have before, right here, has to equal the amount of momentum after the collision. Okay, so before the collision, we know that the momentum was 5.5 kilogram meter per second. That total, again, this is a total of those two things added up together. It has to equal these two things added up together. So we'd have 0.25 kilograms times our velocity. We don't know what the velocity is, so we have to divide both sides by 0.25. And it comes out that the velocity of the 8 ball afterwards is going to end up being 22 meters per second. It kind of makes sense too that if the 8 ball was resting, it has the exact same mass. If all of the momentum from the cue ball was given to the 8 ball, it would have the speed or the velocity of what the cue ball had ahead of time. Okay, we'll go over to question number 2. Question 2, you have a medicine ball is thrown. So here's my medicine ball. Okay, and it says it has a mass of 4 kilograms. And it's being thrown. It has a velocity of 15 meters per second. And it's being thrown at a boy on a skateboard. And the kid on a skateboard has a mass of 55 kilograms. And the kid on the skateboard, he's not moving. All right. It says if, now this is the before, right? Before. It says after the medicine ball hits him. Bam. Okay. After the medicine ball hits him, the medicine ball says that it's going to continue moving at 4 meters per second. So my mass here, it's still 4 kilograms, but the velocity now is going to be 4 meters per second squared. And what we're trying to figure out is the kid that's on the skateboard, what is his velocity going to be after he's been hit with the medicine ball? So we have 55 kilograms, and we're trying to figure out what that velocity is right there. Okay, so let's figure out how much momentum we had at the very beginning. You've got your 4 kilograms, and it was traveling at 15 meters per second. So we know that the medicine ball originally had a momentum of 60. The kid on the skateboard was not moving, so he'd have a momentum of 0. Grand total, that means that we had 60 to start with. Now that has to equal the momentum after the collision. So I know that my momentum of the medicine ball afterwards is going to be 16. And I have no idea what the momentum of the kid is because I don't know what that velocity is. So I'm just going to put down 16 plus the 55 kilograms times V, because we don't know what that velocity is. So I need to subtract 16 from both sides. So 16 minus 6, or 60 minus 16 is 44. And we'll have to divide both sides by the 55 kilograms. So the end velocity for this, the kid on the skateboard is going to be moving at 0.8 meters per second, and that would have to be to the right because it's a positive value. Okay. We'll go to number 3. Number 3, you have a bullet with a mass of 0.1 kilograms. Okay. So we have mass 0.1 kilograms is moving at a velocity of 420 meters per second. It's going to hit a target, and that target has a mass of 1.5 kilograms. It's supposed to be a point. Now, the velocity of the target at first, we're going to have to assume is going to be 0. It's going to hit the target, and it says that the bullet is going to be continuing. Now, the bullet didn't lose mass. It says that the bullet's going to continue moving now at 300 meters per second. But how fast is this target going to be moving? All right, the target had a mass of 1.5 kilograms. The velocity of this is what we're trying to figure out. So just like before, we need to figure out what our total momentums are before and after the collisions. Okay. So we have on the left-hand side, the bullet originally would have a momentum of 42 kilogram meter per second. Your target is going to have a momentum of 0 kilogram meter per second. This quantity right here it has to equal what's on the right-hand side. Okay? So you've got 30 kilogram meter per second as the momentum of the bullet after the collision. And then we have no idea how fast the target's moving because, well, that's what we're trying to figure it out. So we have to take your 42 minus your 30. So you got 12 divided by 1.5. So your velocity for the target after it is struck is going to be 8 meters per second to the right. Okay, so we're going to go on to question number 4. Question 4, it says you have a toy truck. All right, so you have a toy truck, and it's got a mass of 20 grams. And it's traveling along the tabletop at 0.5 meter per second. And it's going to hit a car. Now, it's moving in this direction right here. It says the toy car has a mass of 5 grams, and it's heading towards the truck. And the toy car has a velocity of 0.75 meter per second. It says after the collision, the toy truck, it continues in the original direction. Okay, so it didn't lose any mass, 20 grams. It's going to continue in the same direction at 0.1 meter per second. And then the toy car afterwards, it's still going to have a mass of 5 grams, but we don't know what its velocity is going to be. Okay, so we have to figure out what that velocity of the little toy car is going to be. So again, this is before, this is the after. All right, so we need to figure out what these values are. So we need to multiply our mass and our velocity for each one of these. So the toy truck, it is going to have a momentum of 10 kilogram meter per second. We add to that what the toy car is. Now, here's the deal. You have 5 times your 0.75. Your initial gut reaction is going to be to just put 3.75 down. But the problem with this is the toy car is moving towards the truck. So that should be a negative right there. That should be a negative. That momentum before collision has to equal the momentum after the collision. So if you have the toy truck after the collision, that should be 2 kilogram meter per second. And it's positive because it's going to the right. And then the toy car afterwards, we don't know what the velocity is. Okay, so we'll have to take your 10 minus 3.75, and then we need to subtract 2 more from that. You'd have 4.25, and then we have to divide by the 5. So the toy car, after everything is said and done, it's going to be moving at 0.85 meter per second. Now that comes out to be a positive number, so that means that this little toy car has to be moving to the right with that velocity. Okay. You go to question number 5. Question 5. You have a 8.5 kilogram cart. So here's my cart, mass 8.5 kilograms. It says that the cart is traveling at a velocity of 9.54 meter per second. And it says it's in the positive direction, and it's going to have a head-on collision with another cart. And that cart is going to have a mass of 36.8 kilograms. And this cart has a velocity of 0 meter per second with it. Okay. After they collide, now this is the before, this is the after. It says after collision, the first cart, that's the cart that has a mass of 8.5 kilograms, that velocity is going to be 3.57 meter per second. And what you're left with trying to figure out is how fast is this second cart right here going to be moving? All right, what's that final velocity of that cart? So we're going to do the same thing as we've done before. We need to figure out the momenta of every object before and after the collision. And if we're following that law of conservation of momentum, that means whatever we have before the collision has to equal the momentum after the collision. So our first object, that first cart, would have a momentum of 81.09 kilogram meter per second. Your second cart, it's not moving, so it's going to have a momentum of 0. That's the before. That has to equal your momentum afterwards. So if you have your 8.5 kilogram cart moving at 3.57 second or meter per second, it would have a momentum of 30.345 kilogram meter per second. And we have no idea what the velocity is going to be for this other one right here. So we'll take your 81.09, subtract your 30.3, 81.09 minus your 30.345, divide by 36.8. Oh, I just butchered that up. So let's try this again. We have 81.09 minus 30.345 divide by 36.8. You should come up with a velocity of the second cart after the collision being 1 point, let's just round this off, say 4 meter per second is what it's going to have. Okay. And we'll move on now to the inelastic problems, the inelastic problems. Now, in each of these cases that we've had here, every one of these objects bounced off of each other. But with the inelastic ones, these are going to be where the two objects are going to stick together. All right, so number one, you have a boy that has a mass. All right, so here we have a boy, he has a mass of 70 kilograms. All right, and he's riding on a skateboard, longboard there. And that has a mass of 2 kilograms. So I'm going to put in here 2 kilograms because it's a grand total mass. The two things are together. The kid's on the skateboard, so it makes sense that if they're both moving at a velocity of 3 meters per second to the east, that we should take and consider a total mass of 72. All right, now what's going to happen is it says he is going to attempt to jump forward on a skateboard. All right, so here you have the skateboard. The kid is going to jump off forwards like this. All right, so his mass is going to be over here, 70 kilograms. The skateboard, it's going to have a mass like this. And if the kid is going to jump forwards like this, the skateboard is going to have to go backwards like that. All right. It says if his velocity immediately after leaving the skateboard is 3.1 meter per second, what is the velocity of the skateboard afterwards? So velocity of the skateboard is what we're trying to figure out. Okay. So as always, this is the before, this is the after. What we have to do is figure out what our total momentum is before collision and what our total momentum is after collision. So you have your 72 times the 3. It's going to get you 216 kilogram meter per second. Now that's how much we have at the beginning. We know that the skateboard has a mass of 2 kilograms. We have no idea what the velocity is. That's what we're trying to figure out. But whatever its momentum is, added to the momentum of the kid, has to equal that 216. So we go 70 times 3.1 70 times 3.1 get you 217 kilogram meter per second. So if we subtract the 217 from the 216, you've got 1 divided by 2. The velocity of the skateboard would be 0.5 meter per second, but since it's going to the left, our value, even in the problem, we should get a negative answer, meaning that it's going to the left. That's a direction. We go number 2. You have a rifle that has a mass. Okay, so here is the rifle. It has a mass of 7 kilograms. And the bullet inside of this has a mass. So it makes sense, again, if these two things are together at first, that we would have a total mass, okay? It says that, in here, we can throw this into, what's the velocity of that at first? It's going to be 0. It's not going to be, the gun and the bullet, they're not moving, all right? This isn't a drive-by, people. It's just somebody that's out standing still, and then it says here that the velocity of the bullet afterwards, so there's the rifle. The bullet, its mass is going to be 0.7 kilograms. Its velocity after it's fired is 350 meter per second. All right. And what you have to do is you have to figure out what the recoil velocity is going to be for the rifle. Okay. It says, let's just double check. Yeah, recoil velocity of the rifle. So these values, the value of the momentum for the rifle and the value of the momentum of the bullet, it has to add up to be 0 because that's what's on the left-hand side. So I know not M, we'll put 7 kilograms times your V. We go plus, and then we have your 0.7 times the 350, 245 kilogram meter per second. Okay. So I'm going to have to subtract the 245 from both sides. We'll divide that by your 7, and you get a velocity of the rifle being a negative 35 meter per second. So the bullet's going to go this way. The rifle's going to go that way. Okay, recoil. We have number 3. Number 3, you have a 10th grader. He weighs 60 kilograms. Okay, so we have a kid. He's got a mass of 60 kilograms. Says that he is standing on a 7 kilogram ladder. Okay. It looks like he's floating on it, but we have a 7 kilogram ladder. And he's 5 meters high and 1 meter away from a pool. So let's do this. We'll say right here, this is our water. That's our ground. We'll say that our distance from the pool to him is 1 meter. Okay, and he is, what did it say again, his height? His height was 5 meters up in the air. So 5 meters like this, okay? Just trying to diagram this all out. It says if the ladder flies off at, okay, so he's going to push the ladder away, and then the kid is going to go backwards like that, okay? So hopefully he makes it in the pool, right? So now he's got an octopus now. Looks like an octopus with all those legs. Here, I'd get rid of that. So we've got the kid, he's going to jump off, and hopefully he's going to make it into the water. All right, so the mass of the kid is still 60. The mass of the ladder is 7 kilograms. The velocity of the ladder that said was, flies off at 15 meter per second. You got to figure out what the velocity of the kid is here, and then we got to figure out, if he makes it into the pool or not. So, velocity originally of the kid in the ladder is going to be 0 kilogram meter per second. That has to equal the momentum afterwards. So we know that we're going to have 60 kilograms times our velocity. That's going to equal 7 times 15. You've got 105 kilogram meter per second. So this kid, when we subtract 105 from both sides and then divide it by 60, the kid is going to be jumping with a velocity to the left. Ladder goes right, kid goes left, with a velocity of 1.75 meter per second. All right, so that's how fast he's going to be moving to the left. All right, now when he jumps to the left like that, okay, the question is he going to have enough time to make it into the pool? Okay, well, he is 5 meters in the air. All right, so I'm going to change color. So if he's 5 meters up into the air like this, we need to ask ourselves, how much time does it take before he hits the actual ground? All right, now his initial velocity in terms of up and down vertical, if his original velocity is going to be 0 meter per second, we know the acceleration due to gravity is 9.8 meter per second squared. What we're trying to do is figure out what the time is. And we know the distance up in the air is going to be 5 meters. It goes back to our kinematic stuff. And we could take time equals, we'll have, if we go back, we have d equals at squared divided by 2. Okay. And that's because VO was 0. So we go 2 times the distance. So the 2 is going to move over, we divide by the a, and then we have to take the square root of that thing. So we'll have 2 times 5 meters divided by 9.8 meter per second squared. We get the square root of that thing. We'll punch that into our calculator, and I'm going to use, we have square root. We have 10 divided by 9.8. Says that he ends up having like a 1.01 second time for him to fall. So if the time that it's going to take for him to hit the ground is like 1.01 seconds, yes, he has enough time to actually make it into the pool. Okay, especially if he's moving at 1.75 meters per second. That means that from here, he's going to travel 1.75 meters before he actually hits the water surface. And if the water is only 1 meter away, then he's perfectly safe. Not real smart, but he's safe. All right, we'll go to number 4. Number 4 says that we have, in this case, you've got 2 people. So I'm going to put, let's say we have 1. You got a neck on that guy. We have 2. Okay, so you have one mass of 72.8 kilograms. Then you have another mass is 52.4 kilograms, and they are in a rowboat. They're in a rowboat, and that rowboat has mass of 81.6 kilograms, and they're sitting in it, so we're just going to say that the velocity at the beginning is 0. So we know the momentum at the first is going to be 0 kilogram meter per second. So it says the lighter person is going to jump out of the boat. Okay, so the boat still going to be present. The big guy with the super long neck, he's still going to be in there. And the little guy, he's going to jump out of the boat. Okay, so we know that the mass over here, 72.8, that's going to stay there because that's the big guy. The mass of the boat, that's going to still be there. And the little guy, his mass, 52.4 kilograms, is going to be moving over to the right with a speed. Said if the lighter person jumps out of the boat at 7 meters per second, you're going to have to figure out what the velocity of the boat is over here. All right. Now, whatever our total momentum is before, that's what it's got to equal afterwards. So 72.8 plus the 81.6, we have 154.4 kilograms times our velocity, whatever that's going to be. That's going to have to equal 52.4 times 7, 366.8 kilogram meter per second. Okay, we subtract the 366.8 from both sides, divide by 154.4. The velocity of the big guy in the boat is going to be, let's round that off and say 2.4 meter per second. Now that's going to be moving to the left. Okay, so I'm just going to put this negative 2.4 meter per second right there. All right, and there's a reason for that. See, it says for part B, it says now the heavier guy is going to jump into the water to rescue the lighter person. Okay, so we're going to have another little diagram here. See, I'm going to put, let's see, how can I do this? Let's cheat a little bit. See, this right here is how fast that guy is moving, right? So that's what our momentum is now beforehand, before the big guy jumps out of the boat. All right? So if the big guy jumps out of the boat, what is his momentum at the beginning? All right, so we have 72.8 plus 81.6. That's 154.4 kilograms, and they are moving at 2.4 meter per second. So the momentum beforehand, it's going to be negative 370.56 kilogram meter per second. Remember, he's moving to the left. That's why it's negative. Now he's going to jump out of the boat. The boat is going to move backwards. The big dude, as he jumps in with his big neck, he's going to go in to the right like this after the kid. So the mass of the boat is still 81.6 kilograms. The mass of the guy is still 72.8 kilograms. It said that the big guy's velocity jumping in was 4 meters per second. And we don't know how fast the boat is going to be moving backwards now. All right, so we need to figure out what the momentum after the collision is going to be. So we multiply our individual momenta up. So we have 72.8 times 4, 291.2 kilogram meter per second. Okay. We have to rearrange our equation a little bit. Now we have negative 370.6. We need to get rid of that 291 on the other side, so we have to subtract 291.2 from that. Then we have to divide by the by the boat's mass, 81.6. So the velocity of the boat after it is moving even faster to the left, it would be a negative 8.1 meter per second is what it should be. Okay. All right, we go to number 5. This is the last one of this group right here. We have number 5. You have a kid in a boat. Again, a boat question. So here's the kid. He's in the boat. All right. And he's going to throw a package. So here's the package. He's going to throw it overboard. So let's get these masses here. The kid, the mass of this package. I'm going to put MP package because I don't know how many of these are going to be. We have 6.4 kilograms. He's going to throw it out with a speed of 10 meter per second. All right, so the velocity of the package is going to be 10 meter per second. It says calculate the boat's velocity immediately after, assuming if it was at rest. So here we go. I put that in the wrong spot because here the boat is going to be moving at 0 at first. So our original momentum of the kid in the boat is going to be 0. And then the kid in the boat is going to throw that package out. So the mass of the package is still 6.4 kilograms. And the velocity of that package is going to be 10 meter per second. It says calculate the velocity of the boat immediately after, assuming it was initially at rest. The mass of the kid is going to be 26 kilograms, and the mass of the boat is going to be 45 kilograms, and we don't know what the velocity is. Now, you might look at this and be like, oh, wait a minute. Why didn't he put the masses of the kid, the 26 kilograms, and the mass of the boat, the 45 kilograms over here? Well, regardless of what masses are over there, if it's not moving, there is no momentum with it. So you don't have to really worry about that part. What we do need to be concerned with is the momenta afterwards. So if you have 26 as the mass of the kid, and that was 26, right? Yes. And the mass of the boat is 45. So we know that the total mass of the boat and the kid is 71. And we don't know what the velocity is. And we'll have the momentum of the package. We got 64. So we'll have 64 kilogram meter per second for the package. You have to subtract the 64 from both sides and then divide by your 71. Your velocity of the package, of the kid in the boat is going to be a negative 0.9 meter per second. So the kid's going to go backwards in the boat. Package is going to go this way. Someone's got to take the boat away from that kid. First he's jumping out. Now he's throwing the packages out. Get him out of there. Okay. Go to the last part. You have inelastic ones. And these are going to be where they have two things they're going to stick together instead of separating. The inelastic ones that we had done there before are kind of like explosion ones where you start out as a whole and then it separates. Well, these are going to be where they are going to come together. So you have a girl that has a mass. All right, so here's the girl. She has a mass of 70 kilograms, and she's running east at a velocity of 3 meter per second. And she's going to jump onto a skateboard. The skateboard is stationary, and the skateboard has a mass of 2 kilograms. So we know the momenta there is going to be 0. That's going to be 210 kilogram meter per second. And she's going to be on the skateboard. Wheels on the wrong side. She's going to be standing on the skateboard afterwards. Now, if she's together with the skateboard and they are both moving together, the combined mass together is going to be 72 kilograms because it's her mass and the skateboard. We don't know what the velocity of the girl on the skateboard is going to be. But what we do know is that the momentum of that girl and the skateboard afterwards has to equal 210. So you have 210 divided by 72, that skateboard and the girl will be moving to the right with a velocity of 2.9. We'll just leave it at that. Boy, it's ugly. 2.9 meter per second. Okay. Go to number two. Number two, you have a wrestler is standing at rest. So here we go. We got a wrestler standing at rest, velocity 0. So we know the momentum is going to be 0 of the wrestler at first. It says then you have another wrestler. This wrestler is going to be running at a velocity of 5 meter per second towards him. So we'll say it's going like this. Or you could flip-flop it around. If you drew the running one to the right, our values would just be a little bit different. It says it holds on to him. So what's going to happen is these two, they're going to, like this. They're going to wrap around right like that. Two heads there. There we go. All right, they're going to come together. It says, and the two combine with a velocity of, now since I drew mine going to the left, I'm going to keep it that way. So the velocity is going to be 2.7 meter per second. And mine, since I have it going to the left, it would be a negative. If you leave yours as positive, leave it as positive. Okay, it says the mass of the second wrestler, this guy over here, is going to be 100 kilograms. It says, what is the mass of the first wrestler? Mass equals question mark. All right, so over here on the right-hand side, the after the collision, we know that the mass here is going to be 100 plus, I'm going to put M1 because we don't know what the mass of that first wrestler is, okay? So we'll figure all of our individual momenta ahead of time. We know that that one's going to be 0 because he's standing still. We know the next one is going to be your 500. Now, if you drew yours to the right, it's going to be a positive 500. But the way that I had mine drawn, it was to the left, so I'm going to leave the negative on there. Okay, we go to the bottom one, or the right-hand one. You have 100 plus M times the 2.7 meter per second, negative. So you got 500 divided by 2.7, get you 185.1 blah, blah, blah. And then we have to subtract the 100 from that. So the mass of the first wrestler is going to be 85 point, let's just round this off and say 2 kilograms is what it's going to be. Okay, so all we're doing is just using a little bit of algebra to figure out what that value is right there. Okay, we go to question 3. Question 3, you have a 1 kilogram glider and a 3 kilogram glider, and they're going to collide into each other. So here's one, here's the other. So mass equals 1 kilogram, mass equals 3 kilograms. You're going to be moving towards each other at 1 meter per second on the track. All right, so if both of them are moving at 1 meter per second, velocity 1 meter per second, it says that they're moving towards each other. So let's say this one's to the left and this one's to the right, okay. So we'll have a -1 for the one and a +1 for the other velocity. They collide together. What is their, what will be the speed of the combined masses together? So they're going to stick together like this. Okay, and I'm going to draw mine ahead of time going to the left because you know the one on the right is going to have more momentum because it's got a bigger mass. All right, so we're going to have 1 kilogram meter per second plus over here you got -3 kilogram meter per second. That has to equal, all right, our total mass over here, if they're stuck together, is going to be 4. But you don't know what the velocity is. Oops, put a question mark for that. So we'd have 4 kilogram times our velocity. All right, you got your -3 plus 1, you got 2 divided by 4, so 0.5 meter per second is what you're going to have for your velocity of the two after they collide together. And since it's going to the left, I'm going to put a little negative in there to indicate that it is moving to the left. It would be a negative value. You have number 4. You have a 6-gram bullet. Mass equals 6 grams. Is fired horizontally. So we're going to have a velocity of 250 meters per second into a 1.5 kilogram. We'll have mass equals 1.5 kilogram mass, and it's resting on a tabletop. So we're going to have velocity here. It's going to be 0. And before we ever do anything, I'm going to change my 6 grams. We're going to change that right into kilograms. All right, so we're going to have 0.006 kilograms is what we're going to have. Okay. Bullet's moving like this, and then afterwards, the bullet gets stuck into the block of wood. So, 1, 2, 3, yep. We're going to add this stuff up. We have our mass total afterwards when the bullet is stuck into the block of wood, 1.506 kilograms. And we're left trying to figure out how fast is this block of wood and bullet moving together. Okay, so I'm going to put a question mark here. All right. Our momenta at the first, we need to figure out what the grand total is. I know the block, it's not moving, so the math there is pretty easy. You got 0.006 times your 250. You got 1.508 kilogram meter per second for the bullet. And then the block afterwards, 1.506 kilograms. It's going to be moving at a velocity, but we don't know what that is. So if we divide it out, it's going to come out to be about 1. So if we divide that to be accurate with this, you have 1.508 divided by 1.506. Yeah, let's just say 1. So 1 meter per second is going to be the velocity, and that is going to be going to the right like that. Last question. You have the final speed of a superhero. All right, so you got a superhero here, and they have a mass of 76 kilograms, and they're going to be flying into a train. All right, so here's my train, and it has a mass of 19537 kilograms. And the train is moving along at a velocity of 35 meters per second. So we're going to have it going this way, so that's got to be a negative. It's going to make the train come to a stop. So superhero, train, velocity 0. So I don't even need to put the mass in here, because if the train and the superhero are stopped, we know the momentum after the collision, it's going to be 0. It has to be 0 if it comes to a stop. So how fast does this superhero have to go in order to stop the train? All right. Now let's get the individual momenta first. I know that the superhero, that velocity is what we're trying to solve for. And if I have the momentum of the train ahead of time, 19537 times 35, you got 683,795 kilogram meter per second. All right, we're going to subtract that value to the other side and divide by 76. So this superhero, in order for him to stop the train, he's going to have to be traveling at 8,997 meter per second. I don't even want to think about the force of impact if they stops immediately. Send everybody through the front of the train. But that takes care of all of our problems from that paper. But what you have to do tonight is I want you to work on these problems right here. We're going to say the first 2 pages. You got 1 through 3 here, and you'll have 1 through 7 or 4 through 7 right there that you got to work on.